Thank you. Let me just share my screen here. Okay, are you able to see my slides?
Yes, looks good.
Cool. Thanks. I'm Tristan Weber. I'm a postdoc at NASA Goddard. What I'm going to be talking about now, though, is some work I did as part of my thesis work at University of Colorado. And this work all kind of centered around this idea of studying how crustal magnetic fields on Mars influenced ion escape from the planet. If you're not familiar with the crustal magnetic fields of Mars, these are remnant fields that are locked into the planet's crust from long ago when Mars used to have a dynamo. And what I'm showing here is a map of where those fields are located across the planet's surface. It's not in a uniform spread. They're scattered across the surface. And what we're seeing here is lines showing the direction of the fields, and red is showing where fields are coming out of the planet's surface, and blue is where they're going back into the planet's surface. The result of this is that you end up with a lot of these pockets of magnetic field where you have loops of field across the surface in these scattered patterns. And in some regions, you'll have closed loops of field that will deflect particles and trap particles within those loops. And then between those loops, you have cusp fields that are open to the solar wind and have this ability to focus energy input and have been shown in the past to also enhance escape of ions in those regions. So this resulting situation bears some large similarities to the overall idea we've been talking about in this workshop of studying how global magnetic fields might affect ion escape from planets, and this difference of wondering, does a global magnetosphere, or do magnetic fields in general shield particles, or do they provide these channels of increased escape and energy output? And so a natural question as we're looking at these crustal fields at Mars is wondering, what is the net effect of this system, and how can we study what this net effect is using the tools we have at the planet? Well, one of the tools we have is the spacecraft MAVEN. This has been orbiting Mars for years and years now. And as it does, it's making measurements of the magnetic field, it's making measurements of particle escape and particle outflow. And so one thing we can do is just take actual local measurements of particle energization and escape and compare that between crustal field regions and non-crustal field regions to get an idea of what sort of effects the crustal fields are having as a whole on ion escape. There's been a decent number of studies in the past, many by participants in this workshop, that have been looking at this very question. Many of these studies look at, as the crustal fields rotate around Mars, how ion escape changes at a global level. The idea being, if you look at when the crustal fields are on the day side of the planet, they're probably having a large effect on how the solar wind interfaces with the ionosphere. Whereas when the crustal fields are on the night side of the planet, they're not having the same effect. And by using modeling studies, some of which are shown on the left here, or studies using data, a few of which are shown on the right here, there's been fairly consistent results over time showing that the crustal fields seem to modulate ion escape by a factor of about 1.5 to 3, or somewhere in that region of about a factor of 2. So we're not talking about order of magnitude here, we're talking about a factor of 2 or so. One study I wasn't able to put on here was Kaneko Seki had a poster yesterday that I hope everyone got to see, but the results from that poster were also in the same ballpark of about a factor of 2 difference, a factor of 2 effect from the crustal fields. Okay, so this is all talking about the global ion escape. One thing I'm interested in is also looking at the local escape rates. Because crustal fields aren't actually covering the entire planet, when you look at global ion escape, you're you're factoring in both the effects of the crustal fields and also the distribution of crustal fields across the planet into how those affect the global picture. If we're trying to compare directly to global magnetospheres, it might be interesting also to talk about, just on a local level, how does the presence of one crustal field structure change the escape rates as compared to an unmagnetized region of Mars? So I'm going to quickly show you results that I have that relate to both of these questions of global ion escape and local ion escape. And like I said, we are able to make measurements directly using MAVEN. So what I'm showing here is maps of upward O+ flux for just those ions that are above escape energy and are moving upwards away from the planet. And this is geographic maps across a range of altitudes, going from the lowest altitude they're spaced between 200 kilometers and 1,000 kilometers altitude, going from lowest altitude in the upper left to the highest altitude down in the lower right there. And one thing we can see is that, I should also say these contours that I'm showing on the maps are contours of the crustal magnetic fields and where the strongest crustal magnetic fields are located. One thing we can see is that the fluxes are fairly high, or they are fairly uniform at lower altitudes. But as you move up to higher altitudes, you really are only seeing these high fluxes in the crustal field regions. This has been shown before by previous studies using Mars Express, basically suggesting that the crustal fields are housing higher populations of ions, and that there might be some ways in which that the crustal fields are also helping energize these ions. We'll talk about them more in a second. But one thing you might also notice on these maps is that there's not an amazing amount of data density and that there's a good amount of scatter in the results. So one more helpful way to organize this might be to put it on plots like this. So now I'm showing these same results, except just condensing all of that into one statistical plot. If you just look at the plot on the left, this is once again O+, like we were just talking about. On the x-axis, I'm showing the strength of crustal magnetic fields below the spacecraft as modeled by the Morshauser model of crustal fields. And then on the y-axis, I'm showing altitude. And so like we just talked about before, at lower altitudes, we have fairly uniform ion fluxes, but then at higher altitudes, you're only seeing those ion fluxes in the crustal field regions. So this is giving us an idea of where these particles are gaining enough energy that they could possibly escape, but it's not necessarily telling us whether these particles do escape. Like we talked about, these stronger crustal fields are actually trapping particles and maybe holding on to these ions. If you look to the right plot, this is O2+, it's basically showing the same trend, but you'll notice that at low altitudes, the escape fluxes are much lower. I'm not going to dive into too much detail on these plots here, but the basic idea there is just that O2+, being a heavier ion species, will take longer to get energized if it's following the same process of energization as O+. And so if there's something that's energizing these particles and pushing them up to higher altitudes, O2+ won't reach escape energy and show up on this plot until it gets to a higher altitude. And so we really have to loft these particles up first and then energize them at these higher altitudes. Okay, like I said, these ions aren't necessarily escaping, even if they are at escape energy, because of the local magnetic field environment, the overarching idea of this workshop. And so one thing we have to talk about is what is the magnetic topology in these regions? What is the strength of the magnetic fields? And that's what I'm going to show next. Yes, so this is plots of measured inferred magnetic topology on the same set of axes from the previous slide. So once again, x-axis is the crustal field magnitude, y-axis is altitude, and then in the left plot, I'm showing how frequently we see closed magnetic fields, and on the right plot, I'm showing how frequently we see open magnetic fields. So as you would expect in the lower altitudes and in the stronger crustal magnetic fields, so that's the bottom right of the plots, we see more closed fields and fewer open fields because we're in the strong crustal field regions. And then in the upper left of the plots, you see the opposite, where we're starting to see open fields more often. And then at the highest altitudes, you see less of both closed and open fields because that's where we mostly see draped unconnected topology, which we don't need to talk about much here. But if you'll remember from the previous slides, where we had this energization of particles and many ions traveling upwards with escape energy was in this region of the parameter space where we are kind of transitioning away from closed fields towards open fields. And so we probably have some of these particles are on open fields and can escape, some of them are on closed fields and maybe will not be able to escape. And so we have to factor that in when we're thinking about what these actual escaping ion fluxes are. And then as another important note, this topology only really matters if the particles actually will end up following the magnetic field. If a particle is energized enough that it has a large gyro radius, it will be unmagnetized to that field and won't necessarily follow any topology that we want to prescribe to it. These measurements, I should say, were made using electrons, so they don't necessarily apply to high energy ions. Okay, so as one last measurement for us to make, then we want to figure out if these particles are actually magnetized to the magnetic field. And we estimate that using length scales of the magnetic field. And so what I'm showing here is maps of the estimated magnetization of O2 plus particles at escape energy. And this is using a length scale of the magnetic field that is just taking the magnitude of the magnetic field and dividing it by the gradient in the magnetic field. This is essentially asking how much does the magnetic field change over some short distance compared to the strength of that magnetic field. And so if we take a particle gyroradius and divide it by that length scale, we can get a gauge on whether or not the particles will actually follow the magnetic field. So spots that are blue on these plots are showing you where particles would be strongly magnetized. Spots that are red are showing you where particles would be strongly unmagnetized. And then the transition is in white, essentially, at a value of 1. If you once again put this on that same scale, the same parameter plot we've been showing before, we can see that, as we would expect, ions are only strongly magnetized at low altitudes and in the strong crustal field regions. And basically everywhere else, if you have a particle at escape energy, it may, in fact, be escaping regardless of the field topology. So putting that all together, we now have measurements of escape flux. We know that where we're measuring these escape fluxes, particles aren't necessarily always tied to the magnetic field that well. And so we have to introduce some parameters here to make our estimates of ion escape. Going through that, what I've done for this study is taken the magnetic field and divided it into 3 different sections, which we'll call weak field, medium field, and strong magnetic fields. That's in green, blue, and red here. And then I'm also going to just look at the altitudes at which particles would be actually escaping from the planet, where we're seeing these high escape fluxes. If you look at where those boxes would fall on this other plot to the right, you can see that none of those are particularly strongly magnetized regions, but they're more of partially magnetized regions in terms of how well the particles will follow the magnetic field. So to make these estimates, I'm going to say that in weak field regions, particles are fully unmagnetized. And so regardless of the field topology that we measure, these escaping O2 plus ions and O plus ions will fly away from the field. Will just fly away from the planet because they have enough energy. In the medium field regions, the particles are only partially magnetized. So any particle we measure on an open field, I say, is going to escape. On a closed field, I'll say it has a% or alpha percent chance of escaping. And then on the strongest fields, I'll have another parameter beta that I introduce with the same idea. In the strong field regions, on open fields, particles can escape, but on closed fields, they only have this beta parameter percent chance of escaping based on this partially magnetized regime we're in. So if you throw that all together and just put it onto one plot here, using those measurements we made of the fluxes and using alpha and beta just as free parameters here, this is the full span of ion escape measurements that we would measure for the global picture of Mars. So we also have to factor in how much area is covered by the crustal magnetic fields to make this calculation. And as you can see, this entire span of results is about a factor of 1.5 or 2, which is in agreement with previous results like we talked about, the crustal fields seemingly only having an effect of about factor of, about 2 or so. The dashed line that I've put on this plot would be the escape that would result if you didn't have any of the medium or strong crustal field regions and just took the weakest crustal field regions, that's essentially just induced field, and applied that to the entire planet. So under most conditions, we would see that the global ion escape is not affected that much. And in addition to that, under most conditions for alpha and beta here, the crustal fields are decreasing ion escape by some slight amount, which is in agreement with previous modeling studies. If we also just want to ask, what about the effect on local ion escape? This is mostly just a comparison between these different regions of parameter space that have mapped out here. So if we take our calculation of, if we take our calculations of the escape flux in the green box, in the blue box, and in the red box as a function of alpha and beta. That's what's shown in the right here. This is escape fluxes, and essentially all of the main takeaway here is that in order for these crustal fields to have an effect of increasing ion escape, it would have to have all the particles be significantly unmagnetized. Under most conditions, these crustal fields seem to be decreasing local ion escape, and also this entire range of an effect they have is about an order of factor of 4 or 5. Or 5 or 6.
Sorry,
so,
please pay attention to the time.
Yep. I think this is the last slide here. So these crustal fields are affecting local escape by a factor of 5 or 6, and they need to be very unmagnetized to increase ion escape. So putting that all together in some conclusions, the Martian crustal fields, as we've talked about, affect global ion escape by a factor of about 2. They affect local ion escape by a factor of about 5 or 6. And only with significantly unmagnetized ions would these crustal fields increase local ion escape, as we've often asked as a question for global magnetospheres. In the context of global magnetospheres, how do these results apply to global magnetic fields? That is a question that remains to be seen. Okay, thank you. Sorry if I ran over a bit.
All right, thanks a lot. So we have a couple of questions in the chat. So the first from Eric Lund is, why would the escaping flux decrease with altitude in regions with low crustal field strength? Are the fluxes not normalized for altitude?
The escape fluxes, with low magnetic field strength. So part of it is that those fluxes are per area, and as you move up, you're looking at a larger shell of ions. There's a larger area across where that same number flux will be spread. So if you assume just the same number of particles, then you would expect things to decrease slightly as you move up to higher altitudes. But then the other part of it is that there are always other ways in which an ion could be gyrating back into the planet that I haven't factored in here, or something of that sort. So we haven't necessarily talked about that, but even in those unmagnetized regions, not necessarily everything will escape. I hope that answers the question slightly.
Yeah. Okay, here's another. So is there any way to distinguish the escaping trapped ion populations from your contour maps against the crustal B field distribution?
Against the crustal B field distribution? Is there a way to distinguish the escaping?
Julian, if you want to rephrase that question to make that clear.
Yeah, I think it was just because you mentioned that they have the energy, but you're not completely sure if these are trapped or they're actually escaping. So I was just wondering if there's any way we can distinguish those.
Yeah, and so that we do try to do that using these measurements of magnetic topology, and it's a bit tricky because you don't necessarily know, like we said, whether the particle will have enough energy to really follow the magnetic field that well. But yeah, like we talked about a little previously, using topology measurements and also the estimates of magnetization, you can at least get somewhat of a gauge of whether or not the particle will escape or not. And the basic upshot is, in the strongest crustal field regions at the lower altitudes, you can say with confidence whether a particle will escape, but everywhere else it's a little bit wishy-washy.
Okay. How do you expect field line topology to change during solar storms?
Ooh, yeah, fairly drastically. I have a couple papers that were investigating that. With the increased solar wind pressure, all the crustal field structures tend to get pushed down, and you have a pretty large increase in both open fields and draped field topology that penetrates down to low altitudes and allows for a lot more outflow. And then there's also the constant changes in IMF direction that will inevitably result in reconnection with different crustal field structures. I have one paper looking at that as well. And so both of those together mean that during anything except for quiet conditions, the maps of topology change fairly drastically. Well, I guess it depends on how you view drastically, but they change a significant amount.
All right, I think we better move the rest of the questions to the Slack channel. And
okay, sounds good.
Thanks a lot.